This is the third video from section 4.10, Velocity and Acceleration. Here I'm going to talk about Theorem 117 and Definition 118 at the same time, essentially. So here's our situation. Again, we have a position function. It's a vector-valued function. Its domain is the reals. Its range, or its codomain, rather, is V3. So S goes from R into V3, and as usual, the velocity function is a derivative of the position function. Here we're going to call speed v of t. So this is a real valued function here. This is the speed at time t, which of course is the magnitude of the velocity function. So just keep in mind that the v without the vector, that real valued function, that's speed at time t throughout this video. And so the conclusion of Theorem 117 is how to express the acceleration vector in terms of, well, all of these vectors. We have the derivative of the speed, we have the unit tangent vector, then we have the magnitude of the derivative of the unit tangent vector, and then we have the normal tangent vector. So acceleration can be expressed this way. So why? Well, let's start. What is the unit tangent vector? It's the derivative divided by the magnitude of the derivative. The derivative is the velocity vector. The magnitude of the derivative, this is the magnitude of the velocity vector, this is speed. So now we'll solve for this velocity vector in terms of the unit tangent vector and the speed vector right here. So all we did is we took this, multiplied both sides by the speed function. So the velocity vector is the speed vector times the unit tangent vector. The acceleration vector is a derivative of the velocity vector. Here we have a scalar multiple, right? We have a scalar times a vector. And so we have a product rule for that. We have the derivative of the scalar function with the vector function. Then we have the scalar function and the derivative times the derivative of the vector function. This is one of our product rules that we have for differentiating vector-valued functions. That's the acceleration. Then we take this equation, and for the last thing, we multiply and divide by the magnitude of the derivative of the unit tangent vector. And that gives us what we want. Because when we looked at this coefficient, this is what we were looking for. And so, let's see, this vector divided by its magnitude is the unit normal vector. And so we have this conclusion. It's really just properties of the derivative and some algebra. Which brings us to definition 118. This coefficient here is called the tangential component of acceleration. And this coefficient here, the speed times the magnitude of the derivative of the unit vector function, that coefficient is called the normal component of acceleration.